Let's do a few series manipulation type things. So, example here. Write the following series as a function that starts at n equals 0 instead of n equals 3. Now, there's not just one way to do this, but here's kind of a way that you can work with this, okay? It starts at n equals 3. So what you can do is you can kind of do a substitution, right? So instead of n being 3, you can say, well, I want I to be what? To be n minus 3, right? Because then when n is 3, I is 0. Does that make sense? So if I write this in terms of I, the I will begin at 0 because when n equals 3, I equals 0, right? Okay. And then once you do that, then to switch everything else, you can take this thing and you can solve it for n. So n is equal to I plus 3. And you can substitute that in all of the other places, okay? So n plus 1 will become I plus 4. A sub, that'll be I plus 3 minus 1. I didn't write that here, but that would be I plus 3 plus 1, right? And then x plus 5 to the I plus 3 plus 2, which is, oh, by the way, when n goes to infinity, so does I, so it's still infinity. Then it's I equals 0 to infinity of I plus 4, a sub I plus 2, x plus 5 to the I plus 5, okay? And that's kind of all there is to it. And it's typical that if it started in n, we really should go back to n. This does not matter all that much, but a sub n plus 2. We're typically going to have more than one series, and we're going to want to kind of put them all back together. Now, here's kind of the thing to think of, okay? When this one goes down, this one goes up. So essentially, whoops, as I take this one and send it down 3, I'm going to take all of these things and send them up 3. So n plus 1 is now n plus 4. And minus 1, I can send that up 3 is now n plus 2. N plus 2, send that up 3 is going to be n plus 5. So you can kind of do this in your head once you get used to it. But here's a way to kind of make it all nice and mathy until you've done a few examples and are comfortable. Okay? Good. Next one. What about the other way? So let's do it at n equals 6 instead of n equals 3. So let's go the other direction now. Okay, so I want to start it a little bit later. So I want I to be n plus 3. So that way when n equals 3, I equals 6, right? Good. And then n is going to be I minus 3. So now it's going to start at 6 and go to infinity. And then this becomes I minus 3 plus 1, a sub I minus 3 minus 1, x plus 5 to the I minus 3 plus 2, which is I equals 6 to infinity, I minus 2, a sub I minus 4, x plus 5 to the I minus 1. Okay, now we're sending this one up 3, and so these all go down. That one goes down 3, right, minus 2. That one goes down 3 to minus 4. That one goes down 3 to minus 1. Okay, so when this one goes up, these all go down. When this one goes down, these all go up, right? That's kind of how you think about it. And we'll send this back to n land. N equals 6 to infinity, I minus 2. A sub I minus 4. I'm sorry, I just said we're doing n and then I didn't do it. N minus 2, a sub n minus 4, x plus 5, n minus 1. Now, it's not very typical that we adjust the beginning index. It's actually more typical that we need to adjust this thing. Okay, so that doesn't really change anything of what we've done, except this is going to be our focus instead of this thing. Okay, so nothing really changes in that. except maybe your initial which way things are going. But after that, it's all about the same, right? So if I want to send this one down, I'll send this one up. If I want to send this one up, I'll send this one down, right? That's kind of how it goes. Okay. Here we go. So suppose that I have two power series functions. I want to add them together. Well, simply add their coefficients. That's it. That's all there is to it. Now, the thing is, these all have to match. So it's got to be x to the n, x to the n, x to the n when these are the appropriate n's. And if they aren't, I need to do some adjusting. So here's an example that we're going to need to do some adjusting for. So let's try to add these two things together, and we'll see what I mean by all of this, okay? Again, once the terms match for the same ends, you just add them all together. And very often, if one starts at a different beginning place, you just sort of peel those off like we talked about in the last video, and then add up the remainders, and you get this thing plus some sort of other terms that don't fit into the sum. That's okay. All right, let's write this thing as a single series. Well, the first thing is this can go in, right? Those aren't part of the n's. So let's write this. N equals 3 to infinity. N a sub n, that's going to be x plus 5 to the what? Okay, so x squared times n minus 4 is going to be n minus 2. And then minus n equals 1 to infinity of n a sub n plus 1 x plus 5 to the n plus 1. Okay. Now, before I add these two things together, I need these to match. Okay, so we're going to make both of these series with n's. Okay, so I want it to be x plus 5 to the n. All right, that's what I want. That's what I want. Okay, now this one, I'm going to send this thing up 2. Okay, so it goes up 2 to get to here. And so I'll have to do both of these as well. So if I'm doing the substitution, right, it's going to be I is equal to n minus 2, right? I want the old n minus 2 to be the new n. Does that make sense? Okay. So then n is equal to I plus 2, and so all of these things become I plus 2's, which are just n's, right? So n plus 2, a sub n plus 2. And then where does it start? When n is 3, 3 minus 2 is 1, so the new one starts at 1. Okay, again, this one's going down 2, this one, this one's going up 2, so this one's going down 2. That's not so bad. Then the next one, so this one's going down 1, right? So over here, I is equal to n plus 1. So that means that n is I minus 1. And so this n becomes n minus 1. The n minus 1 plus 1, so that is just a sub I, which is n. And then when n is 1, 1 minus 1 is 0. Okay. Very good. Okay. Oh, nope, that's n equals 2. I'm sorry. I went the wrong way. This is n, right? N plus 1. So that starts at 2. All right. So, can I add these together yet? And the answer is no. This one has an extra term in it. Now, on this one, I actually get to cheat a little bit here. So, watch this. N equals 1 to infinity of n plus 2, a sub n plus 2, x plus 5 to the n, minus the sum, I'll leave that blank for a second, n minus 1, a sub n, x plus 5 to the n. All right, now it used to start at 2. I wanted to start at 1. Now, what is the value of this expression when n is 1? Well, that's x plus 5. That's a sub 1. and that is 0. So actually, if I just manufacture and say, hey, start this thing at 1, I haven't broken anything, right? This is still okay to do. This actually happens somewhat regularly when you're dealing with derivatives because of the n minus 1 we've got going on here. And starting at a term earlier is just adding the 0th term. Anyway, so here we are. We have these start in the same place. The powers of the terms match. And so I can just say this is the sum n equals 1 to infinity of a bunch of junk times x plus 5 to the n. And what's the junk? Well, the junk is n plus 2, a sub n plus 2 minus n minus 1, a sub n. And there we go. I've written it in a single series. Cool. What about something like this? Now, the directions are to write as a single series in terms of x minus 2 to the n. Okay, well, what am I going to do? The problem here isn't so much this thing as it is this thing, okay? If that were an x minus 2, then I could just sort of send it in, but it's not. And so I'm going to have to fix that. And we've seen this trick before in this class. I'm going to write it as x minus 2 plus 2 times that whole series. Series stuff x minus 2 to the n plus 1, right? And then this is going to be x minus 2 times the sum of the series stuff x minus 2 to the n plus 1 plus 2 times the series, right? I'm going to distribute this thing to the term and this thing to the sum, not terms, to the sum, and this thing to the sum. And so plus 2 times that, right? Let's go ahead and fill it in now. N plus 2 squared. I cheated a little too much. A sub n equals 0 to infinity. N equals 0 to infinity. N plus 2 squared, a sub n x minus 2 to the n plus 1. This is why I didn't start by adjusting this one, because I was going to have to do some more adjusting anyway. Now this thing goes in, and I get n plus 2 squared, a sub n x minus 2 to the n plus 2. Plus the sum n equals 0 to infinity of 2n plus 2 squared, a sub n x minus 2 to the n plus 1. Okay, now I'm kind of in the land of the previous problem where I have two different series with different exponents on them, and I need to kind of combine them. So what we'll do is this one needs to go down 2, right? So that's going to be, the n plus 2 will be n, so n plus 2 is n. N is right here, so let's see. So if that's going down, that's going to be a sub n minus 2. And it'll be x minus 2 to the n. All right, again, think right here. I is n plus 2, and so n is I minus 2, right? I minus 2, there it is. Now, those one all went down, and so this one starts up, right? And again, if you want to kind of play around with this here, when n is 0, n plus 2 is 2, when n is 2, n is 2, right? And those should match. Good, let's do the other one. This one needs to go down 1, so that'll be n plus 1 squared, a sub n minus 1, x minus 2 to the n. All right, that one goes down, and then that one goes down, and then that one goes down. And then this one goes up, n equals 1 to infinity. Okay, now here I don't really have quite such luck. Okay, they start in different places, but when n is 1, I get some stuff here, right? So what I'm going to do is I'm going to just peel that off. So when n is 1 from that term, I get 2 times 1 plus 1 is 2 squared, a sub 0, right? And then I get the exact same two things. N squared a sub n minus 2, x minus 2 to the n, plus n equals 2 to infinity. Right, I took off that first one. 2n plus 1 squared a sub n minus 1, x minus 2 to the n. And now I have a single series. I have 8 a sub 0 plus n equals 2 to infinity of n squared a sub n minus 2 plus 2n plus 1 squared a sub n minus 1. All of that times x minus 2 to the n. And there we go. So this is what I mean about pulling off that one thing that doesn't fit. Sometimes you have to do that in order to put these things together. Very good. Moving on. Some more facts that we're going to need later. Here is the first one. If you have two series that are equal for all x, that's important, okay, because they can be equal for one x, that's not what we're talking about. If they're equal for all x, and starting in the same spot with the same coefficients, so identical with everything except the coefficients, if they're equal for all x, then the coefficients are equal. And specifically, if we have one that equals 0, then it means that all of these a sub n's are equal to 0, right? Now, that might look like something, so what? But these are going to be sort of formulas in terms of n, and so we'll be able to solve for stuff, okay? As kind of a final review thing here, some Taylor and Maclaurin series. So this is definitely some 5b stuff. I'm not going to go too far here. If f has a power series representation at x equals c, then it is of the form f of x equals the nth derivative at c divided by n factorial times x minus c to the n. Okay, that's called the Taylor series of the function at x equals c. And then the Maclaurin series is when c equals 0. This happens quite often. And so the Maclaurin series is the nth derivative at 0 over n factorial times x to the n. This actually is where the e to the x function comes from. And one more definition. A function is called analytic at x equals c if the Taylor series for f of x about c has a positive radius of convergence and converges to f of x. Again, there's some things here that we're not going to go into. Again, positive radius of convergence. These all converge for where it is centered. So this converges at x equals 0 because they're all just 0, right? And there are Taylor series that converge, but not actually to the function itself. If you want to talk more about that later, it's in my Math 5b notes. Okay, I show an example of a series, a function whose Taylor series does not actually converges, but not actually to the function itself, and that's very awkward. So analytic functions do. And there are just kind of a list of Maclaurin series or Taylor series that we should be kind of vaguely familiar with. Here is a list of them. I gave them on the next page here. So e to the x is the common one. We definitely should know that one. Sine x and cos x are going to come up in short order here. These are kind of like the even and odd terms of e to the x, where there's some minus sign issues. And if you play around with e to the ix and I sine and cos, that works. That's kind of fun to do. Okay. Then there's one for ln x and ln x plus 1, and for arctan. Arctan is kind of a cool one. 1 over 1 minus x is neat. It's just the geometric series there. Okay. So I think that is it for review. In the next one, we will move on to actually solving some differential equations. Okay? And I'll see you then.